Hello, welcome everybody to this session on neurogeometry meets geometric deep learning. We're very happy and very proud to be able to organize this workshop. I mean, GSI has a long history of, well, in neurogeometry and geometric modeling, obviously. And lately, with the rise of deep learning, we've seen a lot of this knowledge transferring to the deep learning field, but also in all sorts of directions between neurogeometry, the modeling of how the brain and visual systems work, and also to improve deep learning systems. And we get a really nice lineup of speakers coming up, and I'm very happy to see so many of you in this audience today. Without further ado, I would like to maybe first still mention, by the way, the organizers of the program committee. So if Alessandro Sati, Remco Duits, and me, Erik Bekkers. So the next speaker is from the Technical University of Eindhoven. The speaker will be Gijs Bellaert on neurogeometry and PDE-based neural networks. Please, Gijs, you can come forward. His group team is working a lot on group equivariant methods, and I'm looking forward to see more about the content of your paper. Yeah.
Okay, thank you for the introduction, Eric. Okay, so my talk will be about neurogeometry and PDE-based neural networks, and more specifically about the link between them. Okay, I'm going to start with some elements from neurogeometry, because I assume not everyone is familiar with neurogeometry. Okay, so there's this paper by David Field, and I looked at pictures like this. So it's just a grayscale image with a lot of random line segments, randomly orientated. And if you look long enough at this picture, something might jump out. It should be this contour. I hope you found it. So that's weird, right? So that's just a picture with some random orientations, but the visual system picks out one contour. But I also looked at pictures like this, and if you look long enough at this one, you won't find a thing because the curvature is too high. And you have this picture, and you won't also find anything, but because the orientations are exactly 90 degrees off. So what I hypothesize is this association field. So the idea is that the visual system wants to connect local orientations, and this is a picture of how it wants to connect these local orientations. In the middle we have such an orientation. The lines indicate possible extensions, and the grayscale background indicates the likelihood or the willingness to connect. So white is a lot of, it wants to connect, and black means no, don't connect. Okay? So I made this little animation that tries to make it clear how then the visual system uses these association fields. So first, the orientations need to be identified at least. And then you can place the association fields. And where the association fields touch, well, there must be a contour. And that's how a contour is detected. Okay. Now the next thing. There's a paper by Bosking and others. And they analyzed the visual cortex of a tree shrew. This is a tree shrew. And they made it watch TV, in a sense. And it was really boring TV, because they made it watch a line segment. And then they looked at the brain, at the visual cortex, and they watched the activation of the cells there. So when it watched this orientation, the activation was like this. But if the orientation was like this, the activation was like that, etc., etc. So they hypothesized that the visual cortex has orientation selective cells, so that are cells that only activate when a certain orientation is viewed. Okay. So now for the actual neurogeometry. So given the existence of these association fields and orientation selective cells, Petitot, Siti and Sarti imagined the first part of the visual cortex as a lift to a high-dimensional space. And this high-dimensional space is the space of positions and orientations, denoted with M2. So the space consists of triples, x, y, and theta. X and y indicate a position, and theta indicates a orientation. Now, what does this mean? I made this animation. So again, you can identify the orientations in the image, but then you introduce this third dimension, the orientation dimension, and you placed the orientations at the right place. Okay, so why would you want to do this? Why do you introduce this new space? Because in M2, you can endow M2 with a Riemannian metric. So this is the metric. The intuition here is that this metric, okay, so imagine a local position orientation. The W1 parameter indicates how expensive it is to move forward. W2 indicates how expensive it is to move sideways, and W3 is how expensive it is to change your orientation. And now with this metric, you can do the following. I've drawn some association lines here, right? Remember that picture? And I can lift these lines to the high dimensional space in the obvious way. Now here on the top right, I've shown Riemannian spheres, so that are isocontours of the Riemannian distance in this high dimensional space, determined by the Riemannian metric. These are the isocontours. And I've projected these isocontours also down onto the xy plane. And now these pictures, you can overlay them all together, you get this. So the idea is that there's a definite connection, or at least there can be made a connection between association fields and lines and Riemannian distance and Riemannian geodesics in this high dimensional space. Okay, so that's the neurogeometry. So, with this, this high dimensional picture, I remade the animation from previously. So again, identify the orientations, introduce the third dimension, the orientation dimension, place them appropriately. You place the association fields, which are now Riemannian geodesics, and you can complete the line and project it down again. Okay, this is neurogeometry. Now let's see what PDE-based neural networks are. So I guess you're all familiar with a standard CNN layer. You have multiple channels. Every channel is convolved with some kernel, then you do some max pooling and activation function, and then these channels are mixed together again with some affine transform. Now, a PDE layer is similar, but you just take out the convolutions and the max pooling and the activation functions, and you replace them with solvers for PDEs. And in this case, we have 4 PDEs: convection, diffusion, dilation, and erosion. This was introduced by Bart Smets in this paper. Okay, so what do these PDEs look like on R2? Okay, so this is the diffusion PDE. I think we all know it. This is the PDE. This is how you solve it. It's with a convolution with a kernel that looks like e to the minus x squared. Okay, and this is how it looks. Okay, everyone knows this. Then you have the dilation PDE. So that's the norm squared of the gradient. The solution method is a little different. In this case, it's a morphological convolution. And the kernel looks like that. The PDE looks like this. And there's also erosion, now with a minus sign, and it looks like this. Okay, so these are the PDEs that are used in a PDE-based neural network, but where are the parameters? Well, the parameters are hidden in the metric, because you can choose a metric on R2. So in this case, I've chosen the metric here. It's a 2x2 positive semi-definite matrix. And with this new metric, you measure distances differently. You measure it like this. And then here, I've plotted isocontours of this distance. And now we can look again at the effect of the PDEs, but now the effect of the PDEs is changed by the metric. And now you see that the diffusion only diffuses in the direction of the metric. It's the same thing with dilation. The dilation only dilates in the direction of the metric. It's the same with erosion, only erodes in the direction of the metric. So you can change the workings of the PDE by just tuning the metric parameters. Okay. And now we're ready to relate neurogeometry to PDE-based neural networks. So first off, you just saw the PDEs on R2, but the PDEs also work on M2, this high-dimensional space. So you can make a PDE-based neural network on M2. That looks like this. The problem, the data set here is, again, images with random local orientations, and the goal is to find the contour. So the network looks like this. You lift it, You apply the PDEs, and the metric parameters are learned. You get some processed image. You project it down again, and that's the result of the neural network. Okay, so how do these PDEs look in M2? Again, you have the metric, and these metric parameters are tuned during learning. The isocontours look like this. So what does the diffusion look like? I've put a little blob of mass in the middle here, of the high-dimensional space, M2, and I let it diffuse. So again, you can understand the effect of the PDE by just looking at the isocontours of the Riemannian distance. So that's pretty intuitive. It's the same thing with dilation. And it's the same thing with erosion. Okay, so that's how the PDEs look like in M2. And now we're ready to make the link between neurogeometry and PDE-based neural networks explicit. PDE-based neural networks employ diffusion, dilation, and erosion. In M2, these PDEs look like contour blurring, extending, and sharpening with an association field, right? Because the association field is directly related to Riemannian spheres, Riemannian distance, Riemannian geodesics, and these determine the effect of the PDEs. The shape of the association field is determined by the metric parameters, and the metric parameters are learned during training. So here I have another example. You have the image, you lift, you dilate with this association field or this metric, and you can project it down again. So yeah, remember this association field picture from earlier. You see it right there, and you see it right there. Okay, so that's the link. And now you might be asking why these PDEs specifically, right? Because I just gave you these 3 PDEs, but why these? Okay, so that's the next part. But first I have to explain a little bit about semirings. Okay, so what is a semiring? Semiring is just a set with 2 binary, associative, and cumulative operations. We call them plus and times, but they're not the classical plus and times. With the standard rules, basically. So it's like a ring. So times distributes over plus. Okay. Both operations have an identity element. The additive identity annihilates with multiplication. So it's basically a ring, which you just don't necessitate the existence of inverse elements. Okay. And we've already seen 3 examples of semirings. We've seen the linear semiring, so that's just the normal real numbers with normal addition, normal multiplication. But you also have seen the tropical max semiring. So that's also a semiring over the real numbers, but now where addition is the maximum and multiplication is addition. So that's kind of confusing. And there's also the tropical min semiring. So that's where addition is min and multiplication is plus. Okay, and where have you seen these? You've seen these semirings in the solution of the PDEs. So with diffusion, the solution was a convolution where the integral can be, the integral is like a sum, and you multiply the kernel with the initial condition. Dilation was this morphological convolution, so the supremum is like the maximum, and the kernel is added to the initial condition. And with the erosion, you have an infimum and again a plus. So this is where you've seen these semirings before. Okay. This is from our actual submission to the conference. Okay, so let phi t denote the solution operator of one of the discussed PDEs on R2. Okay, so what does that mean? It takes in a grayscale image and it follows the initial condition for t time with the PDE. Okay, now we use these PDEs because the solution operators have nice properties, and they're the following. So these operators are semiring linear. So you're familiar with this in the diffusion case. The diffusion PDE is a linear PDE. And in the dilation and erosion case, it's tropical max linear and tropical min linear. They're all a semiring convolution, where semiring convolution is defined in the obvious way. They all form a semigroup, so that means that evolving the PDE for s seconds and then for t seconds is the same as evolving it for t plus s seconds. It's strongly continuous, so doing a little bit of the PDE doesn't change the initial condition. It's translation equivariant, where translation is defined again in the obvious way. This means that if you do the PDE, then translate, it's the same as translating, and then performing the PDE. It's the same with rotation, and Now the really interesting thing is actually the time scale equivariance. This means that scaling is defined in an obvious way again. So first performing the PDE and then scaling is the same as first scaling and then applying the PDE for a scaled amount of time. This might seem weird, but this is a really strong property actually. So strong, in fact. That comes later. So the properties you have seen in the previous slide can be generalized, not to just R2, but any Riemannian manifold. At least that's what we're working on. And in our submission, we have specifically showed that these PDEs on the Lie group SE2, which is basically like M2, satisfy all these conditions. So this is the semigroup property, for example, the convolution property, the strongly continuous, etc. So we proved that the PDEs have these properties on SE2. But more importantly, these properties can be interpreted as axioms. So that means that if you give me a semiring, I want that my solution operator satisfies these rules, then there's only one PDE left. So for every semiring, there's just one PDE. Okay? Now the last part, why should you use PDE-based neural networks? This is also from our submission. What we did, you have this data set of images from the retina, and the goal is to segment it. So we took 3 architectures, a classical CNN, a G CNN, it's like a CNN, but different, and we took a PDE-based neural network. The parameter count is like this. The results can be seen here. What we did is that we trained the networks for a percentage of the training data and then looked at the performance on the test data set. And what we see is that the PDE-based neural networks need way less data to meet the accuracy of, for example, a CNN. So these PDE-based neural networks are not only parameter efficient, but also data efficient. All right, so this is the stuff we've seen. We've seen association fields, we've seen PDE-based neural networks, we've seen the PDEs on R2, on M2. I've shown you the link between neurogeometry and PDE-based neural networks. I've shown you what semirings are, the properties of the PDEs on R2, properties of the PDEs on SE2, and I've shown you the data efficiency and parameter efficiency of PDE-based neural networks. Okay, so that finishes my talk. Any questions?
All right, thank you very much, guys, for a very nicely done talk. Are there any questions from the audience? Yeah.
Thank you for your talk. Excuse me, I just didn't understand really the link between the ISO contours of the Riemann metric and the story of completing the lines.
Okay, yeah. Let me go back to that slide, if this works. So I think you mean this slide?
Yes. Among, yeah.
So,
that's good.
Okay, so let me go back a little. Okay. So these are just, initially these are just some lines I've drawn, right? And this is just a lifted version of these. These are actually the geodesics.
Yes.
So that's the direct link. So these association field lines are geodesics in M2. Then that's the link, and then here on the top right we just have isocontours of this distance. So the geodesics run perpendicular through these isocontours of the distance, right? Because distance increases on the geodesics.
Okay.
Yeah, does that make clear?
Okay, yeah. No, it's good. Thanks.
Okay.
All right.
First of all, fantastic talk. It was like very clear. I guess the question would be about the training strategy. Like, so you're trying to learn the metric with this PDE-based system.
Mm-hmm.
Is this something supervised where you provide the final contours, or does this arise from some kind of unsupervised objective?
It's supervised learning, yeah. We just have input images with these random orientations, for example, and just the output is the contour. And it's, we also trained on these segmentation data sets, so it's always supervised learning.
Great, cool, thank you.
All right, I think we have time for one more question, and then we move on.
Yeah, thank you for the talk. So now in this work you applied everything to images, then you lift them, so basically you work on M2. Do you also see applications of the same model, for instance on signals on graphs or on other type of manifolds?
As long as you can define the PDE on that space, that might be an application, I would say. One example would be to work in an even higher dimensional space. So we're working with a space of positions and orientations, but you can also work on a space with positions, orientations, scales, or even shears. And then the network would also be equivariant, actually, to these symmetries. Yeah.
Okay, great, thank you.
Right, thanks a lot also for the questions in the audience. I'm sure there's plenty more, but guys will be around, for the rest of the day, and so we can use maybe the time over lunch to go into deeper discussions. Maybe you'd like to continue the program with the next talk. Thanks again, guys.